Let's talk about this. Okay, I'm asking you to take the derivative with respect to t this time. Okay, what happens anytime we take the derivative of a variable with respect to a different variable? Remember when we had x squared plus y squared equals 25? If we were finding dy dx, right, we took the derivative of x normal, but when we took the derivative of y squared, we would have to multiply by dy dx, the variable in which we were deriving with respect to. Okay? So if we are taking a derivative with respect to t, the derivative of v is 1 dv dt. Okay. And then I heard some conversations about how 1/3 and pi are constants. So they're just going to stay along for the ride. Okay. R squared times h. Those are two variables, correct? Two different variables. So we're going to have to do a product. Cool. All right. So the derivative of r squared is what?
2r.
2r. But since we're taking the derivative with respect to t, we have to multiply by dr dt. See where this is going? Plus r squared times, what's the derivative of h? 1
dh
dt. Okay, so now what I want you to talk about in your groups, T typically stands for what? Time. That is what it is going to stand for this week. T is time. So if V stands for volume, R stands for radius, H stands for height, T stands for time, what does all of this mean? What does dV dt mean? What does dr dt mean? What does dh dt mean? Talk about it with your tongue. Think about what a derivative means. Think about what a derivative means.
Well, like each of these, so it's meaning like whatever each variable is that's like the ratio or sort of the slope at that point or whatever. So if you solve that.
Okay. Trevor, what are the two different definitions of a derivative?
Instantaneous rate of change and slope of a tangent line.
Okay, slope of a tangent line, instantaneous rate of change. Which one is more applicable here? Instantaneous rate of change. So dV dt, what does it mean? Of the what? Okay. So dV dt means how the volume is changing with respect to time. The RDT is going to represent what? Austin.
Like the RTT. Isn't that supposed to be the radius over time?
Right, so how, like the rate of change of the radius with respect to time. The HTT, how the height is changing over time. Okay? This is what we're doing today. Okay? We're taking what we know about derivatives, and we're going to be able to look at situations where variables are changing and use derivatives to help us find either rates or a measurement, even though things are constantly changing. Okay? So we're basically going to be doing word problems this whole time. I don't want you to have to write down all of the words of a word problem. So I have some notes for you. Okay. Now, this entire unit is the application of derivatives. You had to kind of expect this coming, right? Word problems, applications. Okay, so here are the steps that you need to take every time you have a related rates problem. And they're listed for you on your note sheet. Look at that. Okay, the first thing you have to draw a figure. If they're talking about the volume of a cone, you need to draw a cone. If they're talking about a triangle, you need to draw a triangle. Okay? If they're talking about a man walking away from a lamppost, you need a lamppost, you need a man. Okay? We're going to be dealing with geometric figures, whether 2 dimensions or 3 dimensions, but every time you're going to have a geometric figure on your piece of paper. Okay? You need to draw it. Okay, then you're going to identify rates of change. If they say the radius is changing this fast, then that's your dRdt. You need to write it down and label it. Okay? If it says find the rate of the volume changing, then you know you need to find dV dt. Okay? This is all in your note sheet, guys, at the top. Okay? Then you're going to find an equation. If you have a right triangle and you have 3 sides labeled, then maybe the Pythagorean theorem is a good equation to use. If we're talking about the volume of the cone, volume of a cone formula would be a good equation to use. Okay? With your equation, you're going to take the derivative always with respect to what? T. We're always going to take the derivative with respect to time. Okay? And then we're going to use our bits and pieces of information to plug in and then evaluate whichever piece of information that we need to. Okay? So, here's the deal with word problems, or with related rates. We go through the same process, but there are lots of different types of problems that we can encounter. And so we just need to do a lot of practice and get exposed to all of these different types of problems. Okay? So, the first one, we have a rectangle. The width is decreasing at a rate of 2 centimeters per second. The length is decreasing at a rate of 3 centimeters per second. At what rate is the area of the rectangle decreasing when its width is 4 and its length is 5? Okay? If you have a measurement that is constantly changing, you have to label it with a variable. Okay? No matter what. If you have a measurement that does not change ever, you can label it with a number. But if something's changing, it has to be a variable. Okay? Because at different times, it's going to be a different measurement. So we have a rectangle. What should we draw?
A rectangle.
Since the width is changing, we need to label it as a variable. I'm going to label it W for width. And since the length is constantly changing, I'm going to label it L for length. Let's identify some rates. If the width of the rectangle is decreasing at a rate of 2 centimeters per second, what have they given us? They've given us the derivative of what? The width. So we can label dW dt is, since it's decreasing, negative 2 centimeters per second. Decreasing means we're going to have a negative rate. Okay? And then its length is decreasing at a rate of 3 centimeters per second. What did they just describe in that sentence? Okay. So dL dt.
Who's going under plan?
Oh, they got those little.
Who's under plan, I think. This is the plan.
It can go under plan, yes. Sorry. Okay, now it is asking for the rate of the area. So what I'm going to write down is we want to know dA dt when our width is 4 and our length is 5. Okay. That is all the information that we have from the problem. If we know information about length and width, and we want to know the rate of the area, what kind of an equation should we write for this rectangle? Probably an area equation. Okay? What? Was there a
Are we
question?
gonna like have to memorize all the equations?
Are you saying that an area of a rectangle is equal to?
No, not like that, but like the area of a cone.
The volume of the cone will typically be given to you, but you're going to use it enough that you're probably going to know it off the top of your head. Okay? Like some of the more crazy ones, sometimes they'll be given to you, but like simple geometric shapes that you probably should know, I will not give you. Okay? So, how do we find the area of a rectangle? Okay. Area equals length times width. Okay. We have our equation. Now we need to do what with our equation? Take the derivative with respect to t. So the derivative of a with respect to t is dA dt. LW is a product. So we have the derivative of L times W plus L times the derivative of W. Once we get our derivative, now we can plug in all of our information. We do not know dA dt. What is dL dt? Okay, and we labeled it so we don't have to go back and figure it out. Okay, dL dt is -3. We want dA dt when the width is 4 plus when the length is 5 times dW dt, we labeled as -2. So what is dA dt? -22? And what would our label be if that's the derivative of the area? Centimeters squared per second. Okay? Because we're talking about area changing over time. So we have area over time, centimeters squared over seconds. Okay? Now, this is not where I want you to stop. Okay? This is the answer, yes, but what does it mean? Q, can you describe to me what that means?
Every second, the rectangle increases in length -22 centimeters, or decreases 22 centimeters in length every second.
Okay, thank you for saying decreasing. Okay, our area is decreasing at a rate of 22 centimeters squared per second. That is what your answer means. Our area is decreasing at a rate of 22 centimeters squared per second. Cute.
What kind of like real life situation would you see something like this where you'd have to find kind of equation.
Like a rectangle changing, like an ice cube melting. I guess that's more like a cube.
You seen Star Wars? You know where it's coming in on them.
Yeah.
That's one.
I mean, like, I don't know why you need to pull out a pen and paper and be like, oh, it's decreasing at this rate. Like, what kind of, like, why do you need to know this stuff? I guess is what my question.
You know how to type real fast?
Some of these problems, it's more about the practice than it is about the actual application. This next problem, let's read through the next problem. We're talking about two cars leaving an intersection and traveling at like certain rates. And we want to know like the distance changing between those two cars. Okay? Does that feel a little bit more applicable? We're going to talk about like sand draining out of a cone. Definitely like something that happens out there in the real world, right? Anything that changes constantly, we can apply this to. Okay. I'm trying to think of different situations. Like the ice cube melting. We talk about like people running around the bases on a baseball field. We'll see some of those kinds of problems where like their distances are changing. It's helping.
Yeah.
Okay. Okay. Our next problem. We have two cars leaving an intersection.
Draw two cars.
Okay, you don't have to draw that for cars, all right? You can, but you don't have to draw like cars. Okay, one is going north and the other is traveling east. 30 miles per hour, 40 miles per hour. How fast is the distance between the two changing after 5 minutes? Okay, let's draw our picture. Okay. We have somebody going north. And we have somebody going which way? East. Right? Now, these two cars, are they moving? So their distances are changing. So I can't label them as 30 and 40. I have to label them as X and Y. And then we would have to label the X dt and the Y dt. If this is X, what is the X dt? Thank you. And if this is Y, what's dy dt? And we are looking for the rate at which the distance between them is changing. You want to call this Z? Okay. Larry wants to call this Z. So we are looking for dz dt when our time is 5 minutes. What?
Sorry.
Okay. If everything is in miles per hour, we probably don't want time in minutes. So how many hours is that?
0.083 hours.
Exactly.
It's actually 112 if you want to use 112.
That would be better.
What's that?
Because I think that's a repeating decimal, isn't it? Okay. If it's a repeating decimal, you probably want to write it as a fraction. You do get to use your calculator on all of these problems, okay? If it's an exact decimal, you can write down that decimal. Okay. So this is our information. Now, what is the equation that would relate all of these variables together?
The quantity x squared plus y squared to the.
Okay, so you're using Pythagorean theorem, right? Okay, Austin, let's make this a little bit simpler because that this might get a little messy. It is okay to just write x squared plus y squared equals z squared. Okay, Austin wrote it as a radical. Okay, z equals radical x squared plus y squared. we can just write it as the Pythagorean theorem because we're using implicit differentiation anyway, right? So you want to make these so that your derivative is as simple as possible. Okay. All right. The derivative of x squared with respect to time. Abram, what is it?
The derivative to x. Oh, x. Yeah.
Okay, good. So since we took the derivative of x, and we're doing it with respect to time, we have to multiply by dx dt. Okay? Plus the derivative of y squared. Logan.
2y times dy dt.
And the derivative of z squared. Sammy.
2z times dz dt.
Yep.
Okay. So we can plug in values for dx dt, and we can plug in values for dy dt, and we are looking for dz dt. We don't have enough information written up there, do we? X, Y, and Z. How do we know what X, Y, and Z are? Okay, well, we know we want dz dt when t is 1/12. So if we know that the exact time is when t is 1/12, how do we know what x, y, and z are? Let's come back to our picture. How fast is car X traveling? 30 miles per hour. So how far have they gone after 5 minutes? How do you find that? Distance equals rate times time. Okay? So when t is 1/12, x would be 30 times 1/12, which is what? 2.5, is that what you said? Yes. Y. If I want the distance for y, we could take 40 times 1/12. How will we know what z is? How will we know what z is? The Pythagorean theorem. Sometimes we have to use this equation right here for something besides just the derivative. Sometimes we have to come back to this equation and use it to find other pieces of information. Okay? So z is going to be the square root of 5 squared plus 10 squared. What was it?
20 times 6.
Really? Can somebody double check that for me? Yeah? Okay, 25/6. So now we can come back to here and plug in x is 5/2, y is 10/3, and DZ is 25.6. Go ahead and perform that algebra to get DZ dt isolated.
You want this in decimal form?
Decimal form is fine. What's your final answer? Joe? Like 50 exactly?
That's right.
Is that what you got?
No.
I got 50.
Okay, good. And I labeled it as miles per hour. Was that okay?
I got
Was miles per hour the right label for that? We're talking about a distance changing over time. So we have miles per hour. Does that describe a distance changing over time? It does. Okay? And since it's positive, this distance is increasing or decreasing? I need an answer. So sometimes we have to use our equation to find different pieces of information to be able to plug in once we get our derivative, okay? So that equation we write isn't always just for the derivative. Sometimes we need it for other things as well, okay? Now, since we have 10 less minutes today, I'm going to go ahead and I want to jump to the second one on this page. If we have time, we'll come back up to number 3. Right now, we're going to do number 4. If we do not have time for number 3, I will post a solution on my website so you can look at it. We're not going to get to number 5 no matter what, but I want 4 is going to be more important right now than number 3. Okay. All right. We have sand being dumped on a pile in such a way that it is that it always forms a cone whose radius equals the height. The sand is being dumped at a rate of 10 cubic feet per minute. At what rate is the height of the pile increasing when there's 100 cubic feet of sand in the pile? Okay. If we have sand dumping into a pile, okay, there may be some constraints like we don't want it to get to a certain height or we don't want it to get to a certain width, okay, where using this related rate stuff would be helpful, okay. First of all, we have a cone, and it's our pile, right? Here's my cone. It's not the prettiest cone, but it's a cone. And the volume is constantly changing, means the radius and the height are constantly changing. And so we need to label the radius as R and the height as H because they are variables that are always changing. If you look up at number 3, there is already a picture in number 3. Notice how there is something labeled with a number. That's because that distance never ever changes, and so we can label it as a number. Since height and radius are both changing, we have to label them as variables.
It says that the radius equals the height.
Oh, that would be a good thing to put down, right?
So couldn't you just have the same variable for both the height and the radius?
Yes, yes you could. And we're going to get to that in a little bit, Hugh. Thank you for pointing that out. Okay. Now, the 10 cubic feet per minute, what is that? The rate of the volume. So dV dt is 10 cubic feet. Okay. And we want to know what is the height, what is the rate of the height. So we are looking for the HDT when our volume is 1,000 cubic feet. So I wrote down all the information that I have. Now Q pointed out that R and H are the same. Okay? I'm going to go ahead and remind you that the volume of a cone is 1/3 pi r squared h, which that is a derivative that we already found on in our warm-up. Okay? So I'm going to take a timeout really quick, and I'm going to go back to that slide. When we took this derivative, do you notice how we have a dr dt and we have an r, correct? We really don't have any information about the radius or how fast the radius is changing. So since that is the case, we need to take Q's suggestion and we need to write the radius in terms of the height, because all we have is information about the height. Okay? We don't know what dr dt is. We don't know what the radius is. All we know is radius equals the height. So instead of volume equals 1/3 pi r squared h, we probably want to write volume equals 1/3 pi h cubed, since h and r are the same. Okay. There could be times. Yes. Correct. That's okay. There will be times where you could have a cone problem and they give you like the ratio of the radius and height, where you might have to use that to substitute with. Here our ratio is 1:1. We can just literally substitute radius to height. Okay? So now we can take the derivative. The derivative of v is dv dt. And then we have 1/3 pi times, what's the derivative of h cubed? All right. So let's come back up to our plan here. We know dv dt is 10. Are you okay with me taking 3 times 1/3 to be 1? Are you okay with that? Okay. H, do I have anything written down about H? We don't have anything written down about H. And we are looking for the HDT. Okay. All right. So we plugged in our given information, but we still don't know what H is. Can we find H with what we have? Okay, Sammy, you're shaking your head. Yes, what can we do?
You plug the volume that you want, so 1,000, into the equation that we use to find the cone.
Okay, good. So we use volume equals 1/3 pi h cubed, and we know that our volume was 1,000. So 3,000 over pi equals h cubed. Everyone okay with how we got that?
What is the simplified answer?
To be honest, it's going to be easiest if we just plug it in like this. Or if you figure that on your calculator and keep it in your calculator. Okay, save that number. So now we can plug that in for h. Remember, if you're dividing by more than one thing, that denominator needs to be in parentheses. So if you're going to divide by pi and h at the same time, it would need to be in parentheses.
Wouldn't the radical be squared?
It's h cubed.
You put in a red equation.
Oh, yeah. Like that. Thank you. Sorry, I thought you were talking about when we solved for h. Point 033?
Yes.
If we're describing dH dt, what's our label for that? Okay. If our volume is cubic feet, then our height would be feet, and since we're talking about a rate, in this instance it's feet per minute, since that was the kind of time used to describe the other rates. So the height is increasing at a rate of 0.033 feet per minute. Okay, we have 4 minutes left in class. We don't have time to get through the entire, was that the third example that we skipped? But let's go ahead and read through it and identify everything. And then on the Unit 3 page, I will post a PDF that is just the solution to that problem. Okay? And then if you want to finish it out and compare, you can. Or look at my work and write it down. Does that sound okay? So we have a television camera, even put it in there for you, at ground level, filming a liftoff. Is that a real life situation right there? Okay, the camera is 2,000 feet away from the launch pad. Probably a good idea to be that far away. And S equals 50t squared. That is how we describe the position of the rocket. That's how fast it's going, okay? Or the position, that's the position. Find the rate of change in the angle of elevation of the camera shown 10 seconds after liftoff. Okay? We want to find the rate of change of the angle. So what are we looking for? If our angle is theta, we're looking for d theta dt when our time is 10 seconds. Next question, look at that figure. How can we relate theta S and 2000? Very good. Our equation is the tangent of theta equals S over 2000. Okay. Remember, we can call this 2000 because that distance is not changing. The rocket's distance is changing from the ground, and the angle is changing, so we have to label those as variables. Okay. All right, so this is where I'm going to stop my video.